Okay, sure. Okay. Am I able to present my screen right now? Hello.
Yeah, you are able to present.
Okay. Okay. So let's start with the presentation. Okay, so my name is Kishlay Singh, and I was a former engineer. I was a petroleum engineer. This is a brief introduction about me. And right now I am studying astronomy at IIT Indore. So yeah, so the talk will be a kind of an undergraduate level, so that people of all backgrounds could understand the physics behind general relativity and what it could it actually does, right? The motivation is also that because in most of the MSc courses that is being offered in India is that there is very much less credits that is given to astronomy, astrophysics courses. Like even in great like universities like IIT Bombay, IIT Delhi, general relativity courses are being given in the third or fourth semester, which is the time by a person decides its thesis or on which it is going to work, right? So this is a motivation so that people could actually take up general relativity by themselves and study. Okay, so like every good thing that we do in our lives, like I don't know if you people are are religious or not, but this is something that I we should start with the talk. This is the famous Einstein's field equation. Here is the energy momentum tensor. Don't worry about this. Don't worry about this. This is the curvature of space time. Like it is a famous saying that energy mass energy tells how to curve space time, and space time tells how to move the mass and energy. Okay, so let's start with some basic stuff, right? What we know actually, and we will build up upon that. So we have studied conservation of angular momentum in 11th or 12th class, I guess, right? So since the topic is rotation of black holes, this animation at the right side gives a very nice example of it, right? So what exactly conservation of angular momentum means? Like if there is a star which is rotating at some omega angle or omega frequency, right? So when the radius decreases, when it collapses suddenly, the conservation of angular momentum remains constant, where it will go nowhere. So that's why to hold the conservation of angular momentum, we get rotating black holes in universe, right? We get rotating neutron star in universe. We get rotating white dwarfs in universe. We rarely get a static black holes in universe, right? Okay, so this is just an animation. Like you can see when the masses are at large distances from each other, and when we close it down, when this radius gets closed down, the angular velocity increases at a very high rate, right? So this animation is taken from the Chandra X-ray website, which is basically an X-ray telescope. So this animation shows that there was a big star once, and it suddenly collapses. Why it collapses? Because the radiation pressure, the radiation which was emitted due to the fusion happening at the core, was not able to withstand the gravity forces of the layers of atmosphere of in this star. So it collapses. Right. This results in a creation of neutron star, either a white dwarf or a black hole. So when does a star becomes a black hole? What criteria should it have? So turns out to be the mass of the star should be greater than 8 times that of sun. Right. I think many of the people who are watching this, they are already a kind of astro enthusiast, so they might be knowing this kind of facts. Okay. So there are basically two types of black holes. There are spinning ones and there are non-spinning ones. The spinning ones are mostly these black holes which are being found in nature. There are rarely we find non-spinning black holes. Like suppose in M87, the picture you may have seen in the 1918 1918 2019 image, that image of a black hole. That black hole has a spinning rate of 90% the speed of light. It means that the surface of the black hole, which is the event horizon, moves at a very high speed, which is 0.9%, 0.9 times the speed of light, right? So let's start with the non-spinning ones. We will start with the simplest stuff, right? So general relativity was given in the year 1915, and the Schwarzschild solution, which is the solutions for this equation, this first equation, this equation. There are many solutions to this equation, but the spherically symmetric solution, which was first given by a guy named Schwarzschild, Carl Schwarzschild. He gave this solution in 1916, and interestingly, he gave this solution when he was in a war between, I don't know, he was sitting in his ditch and doing some physics, and he came up with the solution, right? Just keep mind in dates that I'm talking about, 1915 and 1916. It will be relevant in future slides. Okay, so don't panic with this big ugly equation. This is actually, if you study general relativity, you will absolutely love it. But this is what the Schwarzschild solution is. This is the Schwarzschild metric, right? There is dt square, there is dr square, d theta square, and d phi square. Most of you people are very much aware of the polar coordinates. There is r, theta, and phi, right? There is one more dimension here, which is time. But okay, we will discuss about this in the future slides. Okay, so what I'm talking about here. So let's say that you are at a star. You are looking at a star, right? You are at a position where your position, you are not moving in space. You're not rotating in theta plane. You are not rotating in phi plane. You're just static in space, right? You're just moving in time. Your time is just passing on your watch. So what you will be actually observe, right? So if you put dr equal to 0, which basically means that you are not moving radially, d theta equal to 0, which means you are not moving in the theta plane, and d phi equal to 0, which means that you are not moving in the equatorial plane, which means that this whole thing will become 0. I think most of the people are able to follow this, right? So you are left with this only this term, dt square, right? So just keep in mind, don't mind the calculations that are being here. I just want to come at this particular solution. Okay, so here, d tau equals to 1 minus 2 gm by c square r dt, right? This just look at this equation, and there is two terms here. There is dt and there is d tau, right? Tau is the time. Like suppose you are near a black hole, and there is one more friend of yours who is like a very far away from you, who is watching you at a very far away. You are the one bound to die by being close to a black hole. So suppose, and both of you have wristwatches, right? Both of you have watches at your hand, so that you could read time accordingly. So suppose you integrate both sides, you get tau here and you get t here, right? So suppose you say, suppose 1 minute passes for your friend. Suppose 1 second or 1 minute passes for your friend who is very far away from you. And when you are very much close to the black hole, this r becomes small, right? R is simply the radial distance from the center of the black hole, right? This becomes small, and this whole term becomes small. This whole term becomes big because the denominator becomes so small, because r is so small, and this whole term becomes again small, right? Because 2 gm by c square r becomes a big term, and once it gets it subtracts one unity, the whole terms become small. So suppose one term, suppose your friend has passed a minute or 60 seconds on his clock, but what actually you will feel, it will be like 1 second, 2 second, or 3 second. Time will flow slow for you, right? So, I mean, everyone should. I suppose everyone is able to follow this thing, right? A minute passes for your friend, but on your watch it is like 2 or 3 minutes, whatever your distance is from the center of the black hole, right? So talking about again for the non-spinning black hole, suppose you are still in time, you are not, the time has stopped for you, and you are not moving anywhere in the d theta plane, in the d theta plane, and you're not moving in anywhere in the d phi plane. You're just also, you're not, time is stopped for you. So how will we actually, you will able to describe the geometry, what you will see actually when you are able to, when you are so close to a black hole, right? So this is something, I mean, you people are like most of the people are a big fan of Harry Potter, right? So this is a scene from the Quidditch match club where Hermione, Harry Potter, and Ron were going inside a tent, but from outside it looks so small. But when he enters the tent, it suddenly has a very high volume, and he can move anywhere inside that. This looks like magic in a movie series, but in general relativity, it actually happens. Okay, so look at this formula that we have got here by deleting putting d theta equal to 0, d phi equal to 0, and stopping the time basically, which means dt equals to 0, right? So upon simpler calculations, we get something, we get a formula which is something like this. Don't worry about the how I got this, what steps I have taken. Just look at the result that being shown at this particular slide. Okay, so r is the distance which is seen by your friend who is very, very far away from the black hole. Okay, so, and sigma is the distance that you actually travel while being close to the black hole. Okay, so if you integrate both the sides, you get sigma here and you get r here, right? So 1 minus, if you are very much close to a black hole, this term becomes very much big, and this whole term becomes very much small. So this whole terms in turn becomes big. Are you able to follow the math here? It is very elementary math that I'm talking about here. So if a person who is away from a black hole, he says that, hey man, you are about 10 meters away from the center of a black hole. But in reality, when you travel through to the center of the black hole, you will feel like it is like 100 meters, 1,000 kilometers, even 1,000 kilometers is very much possible. It is not something that is not possible. So this is actually what general relativity predicts, right? These effects is also somewhat similar to the spinning ones, right? Spinning black holes. What I have been talking here is for the non-spinning ones, but when you come close to the spinning black holes, the effects are somewhat the same. Look here. This somewhat has been italicized, right? The asterisk marked below the advertisement of a policy that it is subject to terms and conditions. It is the same stuff that I'm trying to perform here. It is somewhat the same, not exactly the same. It is somewhat the same, right? So how we know how black holes influence the flow of time, and so now we know how black hole influence the time and the flow of time and the stretch the space around it, right? So we know that when you get closer to the black hole, time slows down for you, and while the person who's very much far away from the black hole, time flows very much normally for him, right? And when you are able to look at a black hole from very far away, you say that, hey man, the distance from me to that black hole is about 10 kilometers. But when you actually traverse the distance, it will turn out to be like 1,000 kilometers, 10 times more, like 5 kilometer, 10 kilometer, 20 kilometer. The space it will stretch, right? So now let's understand the structure of a non-spinning black hole, right? I'll make you understand like how this image is being created, why this light has been behaving so differently rather than normally it should do. So this is simply a very simple image of a black hole. There is an event horizon. Event horizon basically means a surface where once you go inside, you're not allowed to come outside. Like here, you can go from this point. From here you can move from this point to this point, this point to this point, this point to this point. But in time, when you're outside the black hole, you are always allowed to move in the future directions, right? So means that whatever you are, like suppose we are right now in the outside of a black hole, right? We don't know, we are not right or inside a black hole. So we are always moving in the future. We can't go in the past, right? But once you go inside the black hole, inside the black hole, you're just bound to move radially inside. You can't go from here to here, and move anywhere inside the black hole. You're just bound to move radially inside. There is just one fate for you to come to the singularity. What happens exactly at singularity, that is not being able to be discovered by physicists. What exactly happens here? So the radius at this, what is its radius? What exactly is the radius of the black hole? It turns out to be, it is it is exactly 2 gm by c square, where g is the gravitational constant, mass is the mass of the whatever core it had in its previous life, and c square is the speed of light. It is very elementary, right? So talking about the redshifts, okay. So suppose there's a friend of you, or there's friend of you who is unfortunate to be very much close to the surface of the event horizon, okay, and he has a torch in his hand, and he turns on the torch, and he has a white light that is coming out of his torch. But when, like, suppose, and you are at a very far distance from the black hole, the light that is coming out of the region of the black hole is so much redshifted that its color will change very much. Like, suppose if he has a blue torch here, and he shines out the torch towards you, and you are supposed standing at here, you will probably see a red color, or it will go in the radio band, or whatever stretched part of electromagnetic spectrum you will be here. So this region is also called the infinite redshift surface, right? Like, suppose if a person is starting at here, it points out a beam of light. It will be so much redshifted that you would probably see nothing in real life, right? Okay, so we will talk about the behavior of particles and light around non-spinning black hole. Okay, so again, we will start with some very basic physics concepts. So there is something called bounded orbits, and there is something called unbounded orbits, right? So for examples, like every planet in our solar system is bound, right? It completes its loops. It is making full loops, right? An unbounded orbit is something which the light object is gravitationally attracted towards the heavier object, but the attraction is not strong enough to cause the light object to bend enough to make it full loops around the heavier objects. This is very pretty much a high school definition. I don't think I need to explain anything more on this. So here I have plotted like this graph is for a Newtonian world, right? Suppose there is a planet who is being orbiting the sun, right? In order to be bounded, it has to be below, inside the it has to be trapped in the potential well of the central mass it is orbiting, right? Once you overcome the potential well, you are unbounded. You are able to move away from the gravitational field of the central mass that is being attracted to you, right? Just look at here carefully. Like, suppose you have very high energy, you will not be able to come closer to a distance which is r equal to 0 at the singularity here, because the angular momentum of your will be so high. Like, this graph is for a non-zero angular momentum, right? Your angular momentum will be so high that you will never be able to be come to closer to the center of the mass that you are probably orbiting. Now I could either bore you with lots of equations or could directly show you how it actually looks, right? So before that, like, equations are very boring, right? Even I feel that they are boring, very much boring. But when you see it happening in real life, you see simulations happening, you actually understand what I mean by that. Okay, so I'll be showing you a software which is which was developed by one of my friends whose name is Lamavir Tuleja. He is working as a physics Olympiad trainer in the country Slovakia, and the inventor and the name of the software is GR Orbits. He has gave me permission to show you all people the simulations that I'll be showing here right now. Okay, so I'll be bringing up my simulation, the software here. So I'll be first showing you for the Newtonian case, right? Just make me open the file. Yeah. So I'll first show you the bounded orbits. Right. It is nothing complex here. There is a potential well, which you can see on the right side, and there is a particle who is being oscillated from left to right just because it is not able to overcome the potential well. So in its whole lifetime, it will be orbiting in the same path and make full loops and spending its lifetime here, right? So next thing I'll be showing you is for a circular orbit. Here you can see the particle is exactly at the lowest distance of the lowest point of the potential well, right? So we know that in our basic from our knowledge from basic physics in 11th or 12th class that for a particle to be what do we say that uh, of potential. What exactly was this word? It is said that this point is called the lowest. It is the local minima. This is the effective potential here is minimum, right? And to overcome this, so suppose a particle has overcome the potential gravitational well, so it comes and goes away. It is being unbounded and it can go far away from the mass and it will never come back just because of the fact that it is right now unbounded in the trap of the potential well. It could just easily overcome it, right? So we will overcome this. We'll move on with the presentation. So we'll now talk about the spinning ones. What exactly happens with the spinning ones, right? So as I was talking about the timeline, general relativity was given at the in the year 1915. Carl Schwarzschild gave the social solution in the year 1916, right? And Kerr gave the solution in the year 1966, which is like exactly 50 years of the giving these social solutions. So my point here being mentioning the timeline here is just that the mathematics here is so much complex that it actually took 50 years to develop the solution for us for the spinning ones, right? The actually symmetric spinning black holes. So this is what he came up with with his Kerr solution. This is actually called the Kerr solution. Just don't worry, absolutely don't worry about what these things are telling you. These kind of Greek equations, but we'll able to get a feeling of what it is actually trying to tell us, right? So yes, so we saw in the previous slide that there was this social solution, right? And when A is basically your spin parameter, it tells you how much the black hole is spinning. When the black hole tends to zero, basically means that if the black hole stops spinning, this whole equation becomes something like this, right? It becomes the social solution. The Kerr solution is for the spinning ones, and the social solution is for the non-spinning ones, which basically means A equal to 0, right? So let's have a look at the structure of a spinning black hole. Okay, so this was my attempt at Python to basically plot the structure of a black hole, but I'll not bore you with this 144 pixel image. I'll show you a 4K image, which is exactly this. So you may be asking like, what is this? What exactly the image here it is, right? So when a black hole spins, it no longer remains a perfectly spherical substance. It becomes something like what exactly that shape is, ellipsoid. It is called ellipsoid, like a watermelon. Okay, I bet everyone has seen a watermelon, right, in their lifetime. And this surface is called the surface of infinite redshift. I will explain everything, what it means, what physics is, what exactly here is going on, and when you will be exactly at this place and what you will be feeling here. This surface is called the outer event horizon. This is the inner event horizon. This is the singularity, and this is the inner Ergo region surface. Okay. So we will come one by one. Like this is the whole 3D structure. If I take a piece inside it and take a cross section of the that this particular thing, you will be able to see something like this. Okay, so let's talk about the interesting physics. I mean, this is the most interesting slide of the whole presentation that I'll be showing here. Like suppose you are at this surface of this surface is called the static limit surface. It is also called the infinite redshift surface. It is also called the surface of Ergo region. What exactly is Ergo region? Ergo region is basically the volume which is in the purple shade and the blue shade. Right. Just remember that all of these things are concentric. Right. This blue sphere is able to ellipsoid is able to coincide the brown sphere. This whole purple stuff is able to coincide the whole ellipsoids inside it. Right. So suppose there is a friend. Suppose you are at here. Right. And you are coming close to the surface of the ergosphere. Here what exactly will happen that and just remember this particular thing is all rotating in one direction, right? It is rotating from left to right, this way, right? This way, it is rotating this way. Suppose you are coming at here and you are able to suppose light up a torch, right, in the opposite direction of the spin of the black hole. What you will see, what your friend at a very far distance from you will see, that the light is not coming out of the torch, right? It is just being stuck there. Even when your switch is on, your light will never come out of the torch, just because this space time. I'm using the word space time. Just keep up with that. The space time is moving so much against him that or her that the light itself is not able to come out of the torch. It is just being collected in the torch, right? I'm just giving an analogy what exactly will happen. And once you move inside this purple region, right? Once you move inside this purple region and you are outside of this light blue region, this region is called the Ergo region, right? What the best part of this, what physics it basically shows is that like if you enter here, you cannot stay stationary at this particular point. You have to rotate in the direction of the rotation of the black hole. You cannot stay stationary at here. Whatever, how much powerful rocket you bring, even like in 100,000 years, even humanity develops a rocket which is able to move at like very close to the speed of light. You will not be able to stay stationary here. The spin of the black hole is so much here that you will move along with the direction of the spin of the black hole, right? And this light blue surface is called the outer event horizon. Like in Schwarzschild case, there was only one event horizon, which was the outer one, right? But when the black hole spin, we get two event horizons, right? So when a person enters here, this event horizon basically means that the name itself means that once you go outside, a particle or a photon, once it goes inside, there is no coming back. You are just bound to move radially inward. You can't move outside radially. Your fate is just to move inside and inside till the time ends, right? Till you release the inner horizon. And this event horizon is basically like a bifurcation between the inside of a black hole and the outside of a black hole. Right. When like a person who is outside can never look or go inside a black hole, and if any matter or any particle or any light substance, if it is inside the black hole, it can never come out of the black hole, just because there is a presence of event horizon here. Right. So there is this ring structure. What is this plate-like structure is happening here? There is a disk this disk. The outer disk is the singularity of this spinning black hole, right? It is the singularity. Like in Schwarzschild case, we just got a point at the center of the sphere, right? But when the black hole starts spinning, we basically get a ring kind of structure at the center, and the edge of this disk is the singularity that I'm talking about, right? And here is basically sci-fi stuff. I mean, you people, most of you people have watched Interstellar, but what exactly physics says here is very much haywire. Physics says that when you go inside, you're able to see your own past, and you're able to meet your older self, which doesn't make really sense. And there is another flat universe here. You basically can you will not be able to ever be aware of the horizons. There is no event horizons in this universe, right? So it is. I mean, I think right now I should have opened your minds, like what exactly how mysterious this stuff is, right? But be sure one can never ever come enter the inside of a black hole. You will just be stuck here, and you will be probably die. Okay, so frame dragging effect, also called as parallelizamine. This is a term that has been coined by me. So this animation here is basically I'm trying to show when a black hole spins, right? You frame dragging effect means like if you are outside of a black hole at here, right? It is just normally a normal space time that you are living at here. You are like suppose you are at here. The spin of the black hole will influence you, will push you to move to rotate in the direction of the rotation of the black hole. You cannot you can stay here with some effort, but if you stay still, you are not powering your rocket engines. You are just staying still here. You will be moving along the direction of the rotation of the sphere, right? So this surface basically means that once you enter here, your rocket, whatever the power of your rocket is, you cannot stay stationary here. You will be forcefully be met to move here, right? So that's why the name is given here, the static limit. This is the limit of this is the surface limit where being static, your property, your power of being static in space just goes away. Once you are inside this, you will be forced by the black hole to move in the direction of the rotation. Okay. And why is it called the surface of infinite redshift? Like again, if you are at here and there is a friend which is very much away, far from you, and you have a torch at your hand. Suppose you emit a blue light from your torch, and your friend is very much far away. He will basically see that light is being stretched. He will basically see the light which is coming reaching him is becoming redder. If you are exactly at the surface, he will basically see no light from your torch. He will not see you, because the light is being stored. The photon is being so much stretched that the photon will not be ever be able to climb the whole gravitational potential level of this black hole, right? So the purpose of this showing you this image is that whatever you have seen in your previous animations of black holes is just a black orb which is moving in space. But actually, when nature, what we actually see is that rotating black holes, and the structure it has is very much similar to this, right? So mathematics behind deriving the orbit equations are incredibly complex. Like it is. Like even for me, it requires like it takes a very much. It took me about 2 to 3 minutes to understand the equation, what it is trying to say. But right now, I'm not here to put maths on you people. I'll just show you just make you taste the fruit that general relativity comes out with, right? So before that, I'll show you the gravitational potential of a spinning or a non-spinning black hole. Just see here, right? What I have seen, I probably have seen, shown you in the previous slide, which is this. This graph is basically for the Newtonian world. When you live in a Newtonian world, when you have a high energy, you just go away from the center of the go away from the potential level, and you are unbounded. You are allowed to go anywhere you want, right? But you can never come close to this axis, which is r equal to 0. But when you are around a spinning or a non-spinning black hole, the physics is somewhat different here, right? These dots here, just don't worry about what these numbers are saying. You just focus upon this particular graph, which is 4.5 here, right? the potential well is something like this. It comes down, reaches its minima point, and then increases as r increases. Right. So there is a maxima here. There is a minima here. Right. So at this particular point, there is a stable equilibrium. How you define stable equilibrium? I mean, in calculus, when there is a function and you want to find the minima, you basically get the differentiate the function and put equal to 0, and you get the maxima and the minima point. And again, when you differentiate it, you will basically get on the sign of the second derivative. You basically conclude that is if it a minima point or a maxima point, right? So for a particle to move in a circular orbit around a black hole, it has to stay at this particular point, right? So when you are able to decrease your angular momentum, right? These numbers are basically your specific angular momentum. This graph, potential graph, is for 4.5 angular momentum, and when you gradually decrease your angular momentum, you basically reach a point where maxima and the minima come closer, and it basically becomes 1 point. Right, there is in this particular graph, there is a maxima here, there is a minima here. When you decrease down the angular momentum, you get your maxima and minima closer, and again you get much closer. And when the angular momentum is about 2√3 times of the mr square, you basically you are basically are the closest point to a black hole where you are able to orbit in a circular fashion. Which I'm trying to say here is basically that, like, suppose where is that image of black hole? Okay. Here. Like this image is a very nice image of black hole. I'll explain why this disk, you're able to see the disk. The light is basically bent here. Why light bends? I'll show you a very nice example of how and why this happens. So what I was trying to say, that this is the accretion dust. Here is some dust, there is some clouds, there is some matter which is orbiting this black hole, right? There is some distance, there is some minimum distance at which the accretion disk stops. It doesn't reaches down to the radius of the black hole. It just reaches the radius at which this graph allows, right? So you can see here, when your energy becomes more than this, you're bound to go inside, right? In the Newtonian case, you can see here, whatever your energy was, you cannot ever reach the r equal to 0, because there was this effective potential which is stopping you from reach the r equal to 0 point. But here in the graph which is being predicted by GR, when you have energy to overcome the bounded region of the potential well, you will just go straight to the r equal to 0 at here. So here I have a very nice simulations for you all people to show you. Again, for the spinning, for the non, I will start first with the non-spinning ones, right? So yeah, so spatially, yeah. So here you can basically see that there is right now at here, there is this black hole which is moving, and a particle is moving, taking a loop. They're taking orbits here. In Newtonian case, you were exactly getting a full ellipse here. But there is something called precision, which is predicted by the general relativity. Apparently, the reason why Mercury has the same effect in its motion. I mean, the general relativity was first confirmed by this particular motion of Mercury, because astronomers saw that it was not completing full ellipse. It was just performing this kind of motion around the sun. So this motion was very much explained by Einstein when he gave GTR, general theory of relativity. And next simulation is I have for you is of a particle which is performing a circular orbits. How it is able to perform these circular orbits? Just because of the fact that it is at its lowest point of the potential well. This is at the equilibrium point, the stable equilibrium point of the black hole, the gravitational potential of the black hole. Right here, you can see in the graph, the graph potential, the potential comes to its lowermost point and increases to a highermost point, and it just goes down. Like suppose if I reset this and put the energy of the black hole to be higher than the potential well. Look now what happens, right? It will just go inside and it will just collide inside the black hole. It will just come and has its fate when to reach the singularity. This particular simulation is for the non-spinning one. Now look what amazing things happens when the black hole starts spinning. I mean, the first time I even saw this, like I was like, what the hell it was even happening here? Okay, so this is not this stuff. So yeah, this is a frame dragging effect. Yes, okay. Yeah, look what exactly is happening here, right? So this particle, this black hole is spinning, right? Look at the last second, what will happen to it? Look exactly at the last minutes, like look how it changes its direction, right? It changed the direction because of the fact that the black hole was rotating in this fashion, and this particular mass was traveling in this in the clockwise direction, while the black hole is spinning in the clockwise direction. This gray part is the Ergo region. Once you enter the Ergo region, you cannot ever go in the opposite sense. You need to move in the sense of the black hole, because the spin of the black hole is so much high. It just makes it spin in the direction of its spin. I'll make the simulation run once again. See this particle is able to cross the gravitational potential, the whole potential of the black hole. So its fate is to go inside the black hole. So it basically comes and rotates forever, right? So now I'll show you for a photon. So look at this. The photon was first going in this direction, and when it entered the Ergo region, even light is not able to protect itself from the spin of the black hole. When it enters the Ergo region, the spin of the black hole is so high, the space-time is moving in the anti-clockwise direction so high that the light itself has to change its direction. It's basically performing a U-turn, right? I mean, in what life you will have seen a light performing a U-turn? It is just general relativity in which we are able to see this. See exactly right. Okay, so and the last simulation that I had for you all people is, I mean, what the hell is happening here? Yes, yeah. So photon near peak potential. Yeah, photon bending. Yeah. So look at here. This is normal. This is just a normal black hole. This is not a spinning black hole. The light ray first came from here, and the gravitational and due to the effect of the GR, the light was bent so much that it almost performed a U-turn, right? It was going in this particular direction, and due to the gravitational well of the photon, it just came back, right? Like suppose if I increase the energy of the photon here, its fate is now to go inside the black hole. There is no coming out of it. But if I put inside the gravitational potential well of the black hole, it will perform a U-turn right now, something like this. Okay, so the purpose of this talk was just to give you a feel of how interesting GR is and what exactly it holds. I mean, even for me, my purpose was just to make you feel aware of what interesting physics it holds, GR, right? So here I conclude my talk, and I'm very much open to questions. So if you people have any questions, then please throw away. I mean, you can put it on your on the chat here, and I can. Okay, there are already some questions here. Okay. Okay, so will a particle moving in a circular orbit lose energy in the form of G waves? Well, Yes, this will happen for a particle. I'm talking about a particle, which is basically a point-sized particle, which is it is not a merger happening here, right? There is no big. I'm just talking in theoretical terms. While in even in theoretical terms, the G waves will come, right? But here in this simulation, it is not losing its energy in the form of G waves. It is just having its energy constant. But since it is able to overcome the potential, well, it will just go inside the black hole, and it will has its fate to reach the singularity. No. So I hope it clears. Uh, okay. Like even anyone could turn on their mic and ask me question. I'm very much open to that. Right. Please do it. So. Okay. So can you maybe elaborate on the future cone of a black hole? Okay, so what you are saying here is exactly a future cone, like the light, the cone diagram of the black hole. Like if you're talking about the what exactly happens with a black hole, there is something called Hawking radiation. Like even in a very far future from here, each and every black hole will be radiated via the Hawking radiation, and the black hole will lose its radius uh, and come down. Okay. Okay. So like anybody can open their mic and ask me question. There is absolutely no problem in answering those questions.
I have one question.
Yeah, yeah.
In the first simulation you showed to us before the photon one, why the particle is touching the parent, the blue lined orbit once in every loop.
I'll try to run the simulation once again. What exactly was happening in that?
Actually, you launched a particle and it was taking up multiple loops. It was not colliding inside that black hole. You were explaining the motion through the of Mercury regarding to it.
Okay, I'll turn that once again. Short shield and a particle elliptical. Okay, yeah. So yeah, so here it is. What is basically happened? This is called the precision of the orbits here, right? The ellipse itself is changing its direction every loop, right? So what exactly your question was, like why it is able to touch this blue line here, right? This was your
Yeah,
question.
why it is touching the blue line in each and every loop once for a time.
Because basically here the energy is conserved. This is the huge well. There's a huge gravitational well here, and the energy is not being lost here, right? If the energy was being lost here, it will not touch the blue line. It will just the this particular point of the maximum radial distance will decrease down every loop. But since here you can see in the graph, this red line basically is the energy level of the particle, right? It is not losing, the energy level is not coming down after every loop. It is just saying that it just says having the constant energy. That's why it is able to perform, able to touch that the place that touch the radius at it started from. I hope this clears, right?
Okay. So to predict the motion of such type of particle which is under such motion, it will be very much difficult to predict that thing.
Yeah, by like before 1915, it was very much difficult to even understand what was happening in with the mercury. Like people like astronomers before thought that there is some different planet which is interfering with the motion of mercury. That's why the motion of mercury is so absurd. But later when Einstein gave his theory and made people understand like exactly why this particular thing is happening, it was a validity. It was a tick mark on his successful theory that he had given. Right. It is just that. Yeah, it is very much difficult by your normal Newtonian mechanics to simulate this. This only happens in a GR, in a general relativity thing. Just know that this at the center the mass is very high, very high. It is not something like your planetary mass. It is, and whatever the mass is, even the radius is so small, it is being compacted in such small space that general relativistic effects come into place. Okay, so there's lots of question at here. So can you elaborate on the Hawking radiation? So Hawking radiation is basically when general relativity is a classic theory, right? It is a classic theory. Even if you don't know quantum mechanics, one can start individually on learning general relativity. There is no need of understanding quantum mechanics. But what Hawking did here was he basically played with the laws of thermodynamics and integrated with the general relativity, and he got to know that he basically got to know the lifetime of a black hole and the temperature what the surface of a black hole holds. I mean, this is not my field of expertise. I'm just a GR guy. I study the orbits of particles, and this stuff could be much better explained by people who are working on quantum gravity stuff, right? So, in what matter does the size of ergosphere or event horizon depend on the spin of black hole? That's a very nice question. So here you can see this image. Like if the spin is very high, if the spin becomes very high, this is just the half cross section of the image. This green stuff is the green curve is the ergosphere, orange is the outer horizon, blue is the inner horizon, and the red one is the inner ergosphere surface. So when the spin becomes very small, this whole green stuff becomes closer and closer and closer, and till when it stops spinning, these four surfaces becomes these three surfaces, this green, orange, and blue, the outer horizon, the inner horizon, and the surface of the ergosphere becomes one surface. There is no one will not be able to distinguish with that. But when it starts spinning, the ergosphere, the surface of the ergosphere comes out, and you are able to see some weird physics happening here, right? So okay, so some good resource for yeah. Okay, so I think everyone is able to understand this. If anyone has any question, I can basically answer it. There's no problem in that. Okay, Dushyant, maybe we can stop right now, right? Okay.
Excuse
Okay.
me.
Yes.
Does it mean that for very high spin, the surfaces of ergosphere and the horizon, outer horizon, may intersect or cross each other? Just in case, theoretically.
It will not cross. Like for very high spin, the surface of ergosphere will be very much far away. This particular diagram is for a spin which is like 99.8% of the velocity of the light, which basically means that this outer event horizon is rotating at a speed which is at 99.8% of the speed of light. At such high speeds, this surface comes out of the black hole, which is the surface of the ergosphere. And when the rotation slows down and basically becomes static, this surface, the outer horizon, and this surface and the outer horizon basically becomes one surface, and this inner horizon and the inner ergosphere becomes one surface and basically becomes a point, which is basically the Schwarzschild black hole, the non-spinning black hole, right? So this is basically happens here. So as spin increases, the ergosphere basically becomes wider and wider, and as the spin decreases, you basically your ergosphere and the outer horizon comes closer to each other and becomes one surface. This is what happens here.
Okay.
And yeah, and so basically, any ergosphere of any black hole, rotating black hole, is it escapable?
No. So what that again is a very nice question. There is something called Penrose censorship theorem, right? Which basically prevents this theorem basically prevents the black hole to have a spin greater than the speed of light. Right, there is a limit to the spin of the black hole. It cannot spin at an infinite velocity. Right, there is some limit, which is the speed of light, which basically means that at the equatorial position, this event horizon, the outer region of the event horizon, it is bound to move at a lower speed, which is which is the speed of light, basically, which means that. So the surface of ergosphere cannot escape to infinity. It is just bounded to be here. This case is for 99.8% of the speed of light, which is basically very much high for a black hole. And this green curve can never escape this whole scenario. It is just bound to be here. Why every time I'm saying 99.8%? Because that is the theoretical limit for a black hole to have its maximum spin, right? So what happens to matter when two black holes collide? So we basically get waves. Like suppose there is a 10 solar mass of black hole, and there is another 15 solar mass of black hole, and it collides with each other, and they basically produce a black hole which is like 22, 23 solar masses. Then you will start asking, like, where is the 3 4 solar masses black hole gone? This whole mass of the black hole is being converted into pure gravitational wave energy, right? And it is being transmitted to everywhere in the space-time. Again, this is not my field of expertise. I just what I do basically is to test general relativity at its very high, at very low distances from the singularity, which is basically, I mean, you have seen the black hole image, right, of 2019. At that image, the people who were astronauts were able to confirm general relativity 500 times more than it was like the strength it had before capturing that image. So testing general relativity at this technology like we have right now is very much essential for people who are doing like trying to integrate GR and quantum mechanics on these stuff. So this basically means that GR is still in the game. It is not a false theory, right? So, I mean, any more questions? I'm very much open, or it depends upon Dushyant also. Like if he is able to, yeah.
Hello.
Yes, yes.
Can you please explain the black hole image that you showed?
Okay. I said that I'll be explaining this, right? So this black hole is basically having a disk, right? There is a disk which is in the equatorial plane, right? Forget about what is happening above or down. There is just one plane in the black hole. There is a sphere in the center, and there is a plane in which all the matter and dust particles are orbiting the black hole, right? And it is very hot, very hot, because it is moving at such high speeds that it is emitting gamma rays, X-rays, and UV and infrared and visible light, right? So what is exactly happening here? The particles which is behind the event horizon, behind the sphere of the black hole, is the light is being curved towards us, right? The light which is being emitted from the backside of the disk is being curved so much that we are able to see it from our viewpoint, right? So this image, this particular spot and this particular spot is of the same part of the disk, but we are able to see the curved part of the black hole, curved part of the disk from the upper side of the event horizon, and the lower part is coming from the downward, being curved due to the downward side of the black hole. So we are getting the same image two times, at the below and the above. It is the same image at both the sides, just because the gravity here is so strong that we are able to produce two images of the same disk at the upside and the downside. This is how general relativity plays here. I mean, this is how the first time it was actually confirmed in, I guess, in 1919 by a guy named Eddington. He performed his experiment at a place somewhere in Africa, where he was able to measure the light bent by our own sun in a total solar eclipse. So when he compared the star at the background of the sun at different time of the year when there was no sun into play, he basically saw that the light that was coming from the stars is bent. So that was a very huge like the experimental evidence of general theory of relativity. So that was that. The sun was sun is able to bend light. Imagine what a black hole would have the power to bend. I mean, I have shown you a simulation here, right, of for a black hole where it was able to bend light so much that it just come here, right? See, this is just a particle, this is just a photon which has been traversing near the vicinity of a black hole. This is not even a rotating black hole. This is simply a normal social black hole. It is just coming here and being bent so much that you cannot no longer imagine like what exactly is happening here. So this is exactly happening here in this particular image. The backside of the accretion disk is being refracted here. I'm using the term refracted, but there is no actual refraction here. It is being refracted upside also and the downside also. You are getting two images of the same disk here. Okay. So there is question, we are accelerating upward. Why isn't the Earth expanding? Two objects drop from the height, side by side will move. So you are talking about the idea of space is curved thing. Okay. So this question is something like, this is something what the general relativity is trying to explain. This is something called the strong equivalence principle, and this basically means that when you are accelerating in a suppose you are accelerating in the Earth, or like near Earth, you are inside a box. You will never know that if you are accelerating or you are still or you're starting in space, in deep space, right? So this is what a strong equivalence principle means. So why exactly you are at the surface of the Earth? Because the space-time is, I mean, this will go beyond the objective of this lecture, but even if someone is asking that, I'll answer this. So like the surface is not exactly coming out of the accelerating upwards. It is just that the space-time is coming close to your feet very much, like it is moving downwards. The time curvature is pushing you downwards to stay on the surface of the ground, right? It is just that. So two objects drop from a height side by side will move towards each other. How Einstein came up with the idea that space is curved. So this is just that Einstein knew that there is something wrong with special relativity when that needs to be, when gravity is playing down, it needs to be enhanced, right? I'll just turn on my lights right now. I think this is much better, right? Yes. Okay. So like, how did Einstein concluded that space is curved, right? So he first saw that the gravitational mass and the inertial mass are the same, right? So he saw that, and special relativity was not compatible with the gravitational forces, because we know that from sun we get we see light that is coming like from 8 minutes. It's taking 8 minutes from the sun to reach us, right? So when you go down deep in that, we saw that the special relativity is not complying with the gravitational forces. So he saw that there is some mistake which is happening here. So he then proceeded towards developing a general theory of relativity. It actually took 10 years, and believe me, the maths was not at all developed all by himself. He has very much mathematician at his dispense to consult and come up with the whole theory. If Hawking radiation takes energy out of the black hole, causing event demise, what really happens to the already curved space-time? It will become non-curved. It just become a flat space-time. It is just that when the mass is converted into pure radiation, there is no mass left here and will just become a flat space-time. There is no more saying in that. Okay, so I mean, I should stop here, right? I think I have taken an hour to speak, right? Okay, okay. See, my motivation of speaking here is that giving a talk here is that, like, most of you people are engineers. I myself is an engineer, right? Yeah, Bhavya, like, yeah, radiation will curve space time, right? But when radiation escapes, from the place where at the first place it was black hole, there is no mass left here, right? Every radiation will the mass which is being converted into radiation will escape away from the place where it was first the black hole. So at this particular point there is no mass here. Yes, radiations do curve space time, but it is not at that degree that we are talking about, the mass being that one solar mass, 10 solar mass black hole being curving the space time here. Okay, so oh yeah, so my motivation here for you all people is that I was myself an engineer, but like most of the MSc degrees in this country, in our country, are not very much focused upon teaching general relativity. Even most of the MSc degrees do not even contain general relativity. Even if it contains, it will have even if it contains, it will be in the third or fourth semester. Till then you will be already inclined towards a particular subject, if you suppose condensed matter physics, solid state physics. So my motivation is that please study general relativity, right? There are very great things happening in our physics. Even the last two Nobel prizes have been won to this particular field, right? So in India, if you want to study general relativity, there are many nice places, or you can even study by yourself. I have studied general relativity by myself and applying it in my life. I'm lucky to study astronomy at IIT Indore, where I'm able to do all of these stuff. But if you take, say, suppose you are doing an MSc degree at IIT Bombay, IIT Kanpur, general relativity basically comes in third or fourth semester, and most of the courses there are relating to quantum mechanics, right? So those students are not interested in taking general relativity and understanding what exactly it happens, because the physics is so much nice, and you can actually see what is happening there. In quantum, you cannot see what is happening, but it just I mean I just showing you in this simulation what stuffs are exactly happening here. So I'll take this last question right now. Imagine falling in the black hole in the frame of reference of the falling man. Will he reach the event horizon ever? So suppose you are itself falling like you are bound to go inside the black hole. For you will not even notice that you have entered the event horizon. You will just go inside and you will go to this singularity and you will just die. Okay, you will never notice the crossing of the horizon, right? But the person who is like very much away from you, when you go inside, he will just see you as you have been stuck on the surface of the event horizon. It will and for infinite time you will be just stuck there. But for you, your time will be so slowed down that you will be easily able to cross that event horizon and just come reach the singularity. But for the person who is very much far away from the surface of the black hole, they will just see that you are just stuck on the surface. You are just stuck in space time. There's nothing happening there. Okay, so I think I should conclude right now. I think I'm very much lucky for Dushan to give me, and the PAE, right now its name is Citizens of Science, to give me this opportunity to speak. And I hope you study GR by yourself and take to discover new things right now, because Nobel prizes are being given away like every year to this particular field. Okay, man. Thank you so much. Thank you, Dushan. Okay. Thank you for attending, and I'm very much humbled. Okay. Okay.